Okay, very good morning. So today we will continue with our last chapter for this subject, chapter number 9. So today we will see the internal something related to internal flow. Okay, so this chapter outline, so internal flow in pipes. So we what are the type of internal flows that we can see, and what are the thermofluid principles that we will be using in calculating the internal flow in the pipe. Okay, so 9.1, fluid flow in pipes. Okay, so liquid or gas flow through the pipe or ducts is commonly used in heating and cooling application and fluid distribution network. So we can see the type of pipe and also duct. Okay, so normally pipe will be for liquid, and for gas normally we will use ducts. So we can see that in our daily life. So in our house, so we in our university, yeah, in outside applications. So this thing will be common because pipes and ducts are the common heating and cooling application, and also fluid distribution network that will be available around us. Okay, so it will the main idea of pipes and ducts are to transport the liquid and also the gas and ensure that there's a flow. Okay, the fluid in such applications is usually forced to flow by a fan or pump through a flow section. So usually we will have a fan or pump. So fan for gas, and pump usually related to liquid. So it will generate a force flow. Okay, force flow meaning is artificial flow, something that is generated by this fan and also pump. So the reason why we need to use fan and pump, because the natural flow is not sufficient. So we need to have more power. So we use fan and also pump to create that artificial or force flow. Okay, so friction directly related to the pressure drop and aid loss. So we have seen this in chapter number 8. So what is pressure drop and also aid loss? So friction is directly related to that. Okay, so during flow, so because when a fluid is flowing from one point to another point, so we will have a friction, because we are having the pipe and also duct, and it is a physical part. So physical part, so we will have the friction during the flow. Uh, so the friction is used to determine the pumping power requirement. So based on the type of pipe and also the type of duct and the material that used to construct the pipe and also duct, so we will calculate the friction that it can handle. So if the pipe or duct can handle more friction, so we will only require little pumping power. So if the friction is higher, then we need to have more power to overcome the friction. So that is what are related to fluid flow in pipes. Okay, so we can see here this picture. So we will have a circular type of pipe. Okay, so most of the pipe that we see, it will be circular. Okay, so it has a reason, so I will explain later. So inside, normally we will have the fluid. So usually will be water or anything else, any liquid. So it can be oil, it can be any liquid that will be transferred using a circular pipe. Okay, so inside must be able to handle at least 50 atmospheric pressures. And for gas, so we usually will use a rectangular or square duct. Okay, so the air will flow inside, so we know air will have a lesser atmospheric pressure. Okay, so why circular pipe? Circular pipes can withstand large pressure differences. Okay, so pressure differences, so between one point to another point, so it can handle the larger pressure differences because of there are no angles. So because when we have angles inside the water or the liquid, so it will create more pressure, and after some time, if we use a square type of pipe for a liquid, so it cannot handle large pressure. Can only handle little pressure, because we also will have atmospheric pressure acting on the opposite direction. So circular will be better to withstand large pressure differences between the inside and the outside, okay, without undergoing any significant distortion. Distortion meaning deformation, but non-circular pipes cannot. So that's why non-circular pipes is not suitable to uh, for the fluid flow, for the liquid flow. Okay, and non-circular ducts are suitable for air. So theoretical solutions are obtained only for a few simple cases, such as fully developed laminar flow in a circular pipe. Okay, so if you want to calculate, okay, so we have seen a lot of formulas involved in this subject. So if you want to use that formula to calculate the fluid flow in the pipe, and then we need to have a fully developed laminar flow. Laminar flow is a straight, smooth flow, steady flow. So then it's much easier to for us to calculate. But we need to know that we are dealing with a real life situation where we will have a lot of fluid problems in our daily life. So it can be in the industry, it can be in our house, so it can be in the university or anywhere. So we are dealing with additional forces, additional parameters that we need to understand. So we must rely on experimental result and empirical relation. So we need to test run. So that's why normally uh, the engineers will test run for a few weeks. So whether there's any pressure drops, so is there any additional forces acting? So they will do a experimental testing, and they will have an empirical relation. So they will compare. They will compare with other types of experiments, okay, in order to understand the nature. Because when we are dealing with a real life situation, so we cannot do any mistake. So we need to test on the field. Okay, so we cannot only rely on a closed form analysis solution. So in other words, it's a theoretical calculation. So theoretical calculation is good for our understanding, but in our daily life, so we need to have other types of informations as well. Okay, so the fluid velocity in a pipe changes from zero at the wall because of no slip condition to a maximum at the pipe center. So we have seen this in our previous lecture notes. So this is a velocity profile inside a pipe. Okay, so let's say this is the starting point, and the velocity will develop until it will be in the shape of a bullet. Okay, so why this shape is happening? So at the wall, so at the point where the fluid is touching with uh, the pipe wall, so it will have a condition called no slip condition. So we have seen this before. So at no slip condition, the velocity will be zero. Okay, so that's why here the velocity is zero at these 2 points, and slowly the velocity will build up, and at the middle it will be maximum velocity. So it will form a shape of a bullet. Okay, so if we see the explanation, the fluid velocity in a pipe changes from zero at the wall. Okay, so at the walls, so we have two walls, so it will be a circular, but we just take a 2D image. Okay, so why is zero here? Because of no slip condition, and at the middle it will be maximum velocity because no walls are attached, so no frictions. So average velocity, so we call it as a VAVG. So AVG is average, is defined as the average speed through a cross section. So if we take a cross section of a pipe, it will be circle. So let's say this is the red line, dotted line is the cross section. So at what speed the fluid is passing through this cross section. So that is the calculation for average velocity. So we will add up all these lines, and we will divide into the number of lines to get the value. For fully developed laminar pipe flow, V average is half of the maximum velocity. So we have two parameters here, V max and also V average. So at this point, V max is 2 times V average. So let's say the V average after you calculate is 10 meter per second. So V max will be 2 times 20 meters per second. Okay, or we can take V average is half of V max. So if V max is 20 meter per second, V average will be 10 meter per second. So that is for a fully developed laminar pipe flow. So meaning no more changes, in the pipe flow. Okay, so the value of average velocity V average is at some streamwise cross section is determined from the requirement of the conversion of mass principle be satisfied. Okay, so we know mass flow rate, so m dot equals to rho V average and AC. So if there's some changes, then we can take the integration of this value. Okay, so usually after we have a fully developed laminar pipe flow, so we will just calculate the mass flow rate using this formula. Okay, so laminar and turbulent flows. So what is laminar and turbulent flow? So I think we have covered this in chapter number 6, but I already explained about this earlier. But inside the pipe, so how the laminar and turbulent flow inside the pipe. So we will see today. So firstly, we will see there are 3 phases of flow. First will be laminar. So laminar is a smooth, streamlined, and highly ordered motion. So like you see, so let's say we have a fluid flow inside this pipe. So the fluid is moving at average velocity of V average. So let's say you are injecting a dye. So dye is like a color. So the velocity will push in from left to right. So when you put the dye inside, the dye will move in a straight line along the streamline. So that's why it says laminar is smooth streamline. So this streamline is smooth and highly ordered. So it's not distorted. So it's not having disorientation. So it's just moving in one straight line. So that's why we call it as a smooth straight line and highly ordered motion. Okay, so that is for laminar flow. So let's say we have the same situation. So now we are trying to inject. So we have a flow at the moving that at velocity of average velocity of V average. So let's say you're trying to inject a dye, and after some time the dye is moving in not order motion. So we call it as a turbulent. So turbulent, so velocity fluctuation. So even though the velocity is moving in this direction, it is having some kind like a disordered motion. So instead of moving from left to right, it is moving upward, downward. So it's moving in a highly disordered motion. So that is what we call as a turbulent. And we also have a transition. So transition we know is moving from one point to another point, or one type to another type. So here we have two types, laminar and also turbulent. Transition is the flow fluctuate between laminar and turbulent flow. So in this case, so we can see, so the dye is entering to the pipe. Initially it is laminar, so it's like considered like a straight line. but after some time, it is changing to turbulent. So based on this explanation, so the transition point from laminar to turbulent is around this area. Okay, around this area. So that place we call it as a transition. Okay, so in real life we have seen a candle. Okay, so we have a candle here. So there's a smoke coming out from the candle. Okay, or anything, maybe a cigarette or any application. So after some time, there's a smoke generated. So initially, it will be laminar. So it will be laminar because it will be under the highly ordered motion. But after some time, it will have environmental effects. So the wind changes. It will start to become weak and it start to have a turbulent flow. So, and the point between laminar and also turbulent, we call it as a transition. So transition is at the middle. Okay, so most flows encountered in practice are turbulent. So in our calculations and also lecture, so maybe we can see this laminar flow, but usually the one that we encounter in our practice, so especially when you become engineer, you go to industry, so you will see most of the flows in the pipe will be turbulent. It will be turbulent. It will have some kind of disorder, disordered motion that you need to consider. So if it's only little, then you can neglect. So you can assume that it's not there. But most of the case, if there are highly disordered motion inside, then you need to take into consideration. Because if you are dealing with a mission, so you cannot have at times you have oil, at times don't have oil, so the oil is going elsewhere. So it will create a problem to the machine. So it's not possible. Similar like our car. So our car must have a constant engine oil. If there's a leakage inside, so the flow will not be uniform. Then our engine will become jammed. Then we need to do overall, and we need to, if in a lesser complicated case, we need to change the engine oil. So similar in the industry, we will see most of the flows encounter in practice are turbulent. So we as the engineer, we are responsible to encounter that problem as well. So laminar flow is encountered when highly viscous fluid such as oil flows in small pipe and narrow passage. Okay, so laminar flow normally will be when it is a highly viscosity fluid. So the chances of it to deform is lesser. So especially when we are dealing with oil, so hydraulic oil or the other type of oil, so it will be more viscous compared to water. And when the flow is moving in a smaller pipe, so we assume that it is laminar. Uh, okay, so that will be the case in the real life. Okay, so how we can calculate whether there is a highly this this order these orders in the flow. So we calculate using a Reynolds number. Okay, so 9.21. So what is Reynolds number? I think in previous slides also we have seen about Reynolds number. So we always write RE. So RE. So what is Reynolds number? So the transition from laminar to turbulent flow depends on the geometry, surface roughness, flow velocity, surface and temperatures, and type of fluid. Okay, so these are the factors that affecting so whether the flow will be laminar or turbulent. Okay, so first thing is geometry. Geometry is the shape of the pipe or the shape of the duct. So that's the geometry. Is the surface roughness. So inside the material, the type of material used in the pipe. So whether it is rough or not. So if more rough, so more friction. So it will have more complexity. and flow velocity. So at what speed the flow is moving, the surface temperatures. Okay, so we have seen earlier. So each pipe or duct, it will have outside, the outer surface and also inner surface. So normally the fluid will move in the inner surface. So the surface temperature, the surface, the temp temperature to where the surface is exposed. So maybe in the industry. So let's say the place is very hot or it's very cold, and then it will affect the flow. Okay, and the type of fluid. Okay, so type of fluid, it can be highly viscous or less viscous. So it will, all this will affect the transition from laminar to turbulent. Okay, so the flow regime depends mainly on the ratio of inertial forces to viscous forces. Okay, so Reynolds number. So the Reynolds number is practically calculated by the inertial forces over viscous forces. So what is viscous force? So viscous force is, yeah, internal. Okay. So this is internal. Okay, from the fluid. So what are the viscosity? What are the effect given by the fluid? So initial will be from external. Okay, so external force. So force acting towards the fluid. So it can be the 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 friction from the opposite direction. So flow from the opposite direction. So initial force is representing the external force acting on the body. So the viscous force is the internal force acting towards the pipe or the flow. So if the Reynolds number, you want it to be high, so you reduce the viscous force. So if the internal force is reduced, so the Reynolds number will be higher. And if you want the Reynolds number to be lower, so you need to increase the external force. Okay, so we have seen this formula before. So initial force is rho v average square and d square. D is the diameter. So viscous force is mu v average d. So once you solve it, we will get density v average d over mu. Okay, and this can be converted using this formula to this as well. Okay, so v is the volume. At small or moderate Reynolds number, the viscous force are large. So viscous force is large. So when viscous force is large, so Reynolds number will become lower. So to suppress those fluctuation and thus keep the fluid in line. Okay, so when the viscous force is bigger, so Reynolds number will be lower and it will be more laminar than turbulent. So when the Reynolds number is large, the initial force, which is proportional to the fluid density and the square of the fluid velocity, are large relative to the viscous force. Okay, so what is it actually saying? So when the initial force is larger, uh, the Reynolds number also will be larger because it's directly proportional, and it will cause a rapid fluctuation in the fluid, which cause the turbulence. So because the fluid cannot move in the way it's supposed to move, because the outside forces will be acting upon it, and it cause it to be turbulent. So then we also have a critical Reynolds number, so RECR. Okay, so what is this? The Reynolds number at which the flow become turbulent. So similar earlier, the transition. So transition is happening here, and also it can happen like this also. So initially it will be laminar, then become turbulent, then it will become laminar, then become turbulent. So every time there's a conversion between laminar to turbulent, okay, like here and also here. So we will have a critical Reynolds number. We call it as a RECR. CR is the critical. The value of the critical Reynolds number is different for different geometries and flow condition. So it depends on different shapes of the pipe. The diameters of the pipe. So that's related to geometries and also the flow condition. So whether it's continuous, whether it's steady. So it's all depending on the uh, critical, depending on the geometric and also flow condition. Okay, so in a circular pipe, so usually it will be like this. If the Reynolds number is lesser or equals to 2300, we consider it as a laminar flow. So if the Reynolds number is between 2300 to 4000, we call it as a transitional flow. So meaning is transitioning from laminar to turbulent is in that phase. So meaning the transitional flow is not necessarily one point. It can be one zone. So it can be one range. So the range is 2000 if the Reynolds number is 2300 to 4000. And if the Reynolds number is more than that, more than 4000, we consider it as a turbulent flow. Okay, so you as an engineer, you need to check. So from if for the flow to move from point A to point B, so is it totally laminar or totally turbulent, or it will be having a transitional flow? If transitional flow, how many times? So like in this case, it has 2 times. So it can happen like that in real life. So we need to take point to point. So point A to point B, we need to divide into few points. So depending on our experimental analysis. So I already told earlier. So the flow in the non-circular pipe. Okay, so the pipe can be non-circular. Yes, so like this. So this is more like a dart, but pipe, the tube or the pipes can also become non-circular. Okay, depending, because in our daily life, so we have a lot of requirements. So all these pipes are developed based on the requirements from the customer. So if the customer wants a certain design of pipe, so which is non-circular, then we can calculate using this formula. So for flow in non-circular pipes, the Reynolds number is based on hydraulic diameter. So the hydraulic diameter is only for non-circular pipe. If circular pipe, we can just use the formula earlier. So we have something called hydraulic diameter, or we call it as a DH. Okay, so equals to 4 times the area or area of cross section AC over P. So P is the wetted parameters. Okay, so wetted perimeter means the inside. So the wetted, I think we already discussed this before. Wetted means the surface, the fluid is touching. Okay, so in the pipe, the fluid will be inside. So the inner diameter is the wetted perimeter. So you need to calculate the perimeter for the inner side. Okay, so you can use the formula of diameters, or you can convert it into radius. So it's up to you. So we can have this kind of situation. So which is already given here, the formula. So you just need to replace the values inside. So if it's a circular tube, so circular tube is similar like this. So dH will be equals to D. So for pi, so pi d square over 4 is the area inside. So divide by pi d, so you can get your d. So for circular tube, dH will become is equals to D. So no changes. But other form, so rectangular duct, so you can use this formula. So dH equals to 2AB over A plus B. Square duct. So A is, you can get the value from this picture. Okay, so dH equals to 4A square over 4A. So once you cancel, you'll get A. And channel, so channel will be one side will be open, and one side only certain portion will be filled with liquid. So dH equals to 4AB over 2A plus B. Okay, so these are some of the formulas that already calculated, so you can just use it as it is. Okay, so the entrance region. Okay, so let's say this is a pipe. Okay, so pipe, so it has an entrance part and also the flow. So the pipe in the overall context. So this part we can be divided into few. Okay, so initially if you can see, so the velocity will be the same because it's exposed to the atmospheric pressure. So the velocity will be the same. But over the time, so we can see the velocity profile is greater. So it will be slowly develop until it become like a bullet. So bullet is the one that we have investigated earlier. So this is a fully developed velocity profile. Okay, so fully developed velocity profile. But initially, it will be the same. Okay, so we will see how this from the entrance region until the fully developed velocity profile is generated. So we will divide it into few sections. Okay, so along the while explaining, I will explain based on these figures. Okay, so the first one is velocity boundary layer. So velocity boundary layer is at the side. Okay, so what is velocity boundary layer? So the region of the flow in which the effect of viscous shearing force caused by fluid viscosity are felt. So if you see, initially the average velocity will be the same because it's exposed to atmospheric pressure. But after some time, we can see the velocity started to F shape like D. Okay, D. So it is caused by the viscous shearing force. So there's a uh, shearing force acting at the wall. Okay, because of no slip condition. So we have a no slip condition. So the particles that attach near to the wall will experience friction. So the shape will become like this. The part that not exposed, so it will become more free. So it will become more. So that is the region or the layer where the shearing force is experienced. We call it as a velocity boundary layer. Then we have a boundary layer region. Okay, so it's actually same. Okay, same. So the viscous effect and the velocity changes are significant. So we can see it's already started to form shape. So irrotational flow region. So irrotational flow region is around here. So the frictional effect are negligible. So even though there are particles attached to the wall, but the frictional effect is negligible. Um, so because we are having atmospheric pressure, and the velocity remain essentially constant in the radial direction. So the velocity will be same. Okay. So hydrodynamic entrance region. So from here until here. So what is this point? The region from the pipe inlet to the point at which the boundary layer merges at center line. So this is the uh, So this is the pipe inlet. Okay, so pipe inlet. So pipe inlet. So you will have more atmospheric pressure, but after some time it will start to develop the velocity profile, and after some time the boundary layers merge at the center line. So you start to merge at the center line. So this place from the pipe inlet until this level, we call it as a hydrodynamic. So hydro means water. So dynamic means flow. So flow of liquid entrance region. From here, it will start to pick up. Okay, so hydrodynamic entry length LH. So LH is actually the length from this point until this point. So we call it as a LH. Okay, LH. So the length of the hydrodynamic entrance region. So that's a length LH. So hydrodynamically developed flow. Okay, so hydrodynamically flow in the entrance region. Okay, so flow at the entrance region. This is the region where the velocity profile develop. So at this point, so we call it as a hydrodynamically developing flow. So hydrodynamically fully developed region. Okay, so this is the region. So hydrodynamically fully developed region. So the region beyond the entrance region. So until here is the entrance region. Then from here, we call it as hydrodynamically fully developed region. So we already have the full velocity profile developed, and from here it will be remain the same. Okay, so it will remain unchanged. Okay, so this velocity profile we call it as a fully developed velocity profile, and both of the velocity profile and the normalized temperature profile remain unchanged. So meaning it will be unchanged over a period of time. Okay, so that we call it as a fully developed velocity profile. Okay, in the fully developed flow region of the pipe, the velocity profile does not change downstream. Downstream meaning fluid normally will move from upstream to downstream. Okay, in Malay we call as ulu ke hilir. So it will move from high pressure, higher point to lower pressure, lower point. Okay, so this side, as it moves, it will move towards the downstream. So at the fully developed flow region, so after this velocity profile will be the same. Okay, and the shear stress remain constant. So the frictions on the wall will remain constant. Okay, so if we investigate further, so we can see the pressure drops. Okay, so shear stress, okay, tau, shear stress. The pressure drop is higher in the entrance region. Okay, so at the entrance region, the shear stress will be more, but over time, it will start to reduce. Okay, because of pressure drop. Okay, initially, it will be supported by atmospheric pressure, but after it go inside the pipe, so atmospheric pressure will lose the pressure, then we can see a significantly pressure drop. Okay, so higher pressure to lower pressure, and after fully developed region, it will be constant. Okay, so here we can see at this point the shear stress will be higher, but pressure also higher. So as it goes inside, it will become more linear. So the variation of wall shear stress in the flow direction for the flow in the pipe from the entrance region into the fully developed region. So after the fully developed region, the tau or the shear stress will be the same. Okay, so here we can see LH. So earlier in the picture don't have. So LH is at the entrance region, the length of the entrance region. Okay, so 9 0.3.1 entry length. So the hydrodynamic entry length is usually taken to be the distance from the pipe entrance to where the wall shear stress reaches within about 2% of the fully developed area. So we why earlier in the picture is only we are taking LH from entry region until that entrance region. Uh, so that is because it will reach a 2% of the fully developed area. After that, it will become constant. So hydrodynamic entry length for laminar flow. So we have LH laminar over D. So it will become lower Reynolds number, so 0.05. So this is already calculated, okay, by engineers. So 0.05 Reynolds value. So we know when it's highly ordered, the Reynolds number will be lower. So for laminar flow, so here we only have a 0.05 Reynolds number. Okay, so if you want to calculate the length, you just times with D. Then we can get the length. Okay, so for turbulent flow, it will be much higher. So 1.359. So you can compare the differences, and but the Reynolds number is times by 1/4. Okay, so we can calculate the length. Okay, so this is also already calculated by engineers. Okay, so always L is turbulent, length of turbulent region is lesser than length of laminar region. So in many pipe flow in practical engineering interest, the entrance effect become insignificant beyond the pipe length of about 10 times diameter. So these values we use mostly for our calculations, but in our daily life, so we can approximate for, because will be dealing with mostly turbulent flow. So it will become times with 10. Okay, so we are not really taking into consideration this, but we will be approximating that length based on uh, times 10. So meaning LH turbulent equals to 10 times D, so 10 times of diameters. So that is where we will start our investigation. And along the way, when we have experimental values, we will try to adjust this value. So maybe for that particular region, it will be 9. So or it will be 8, or it can be 11 or 12. So we can adjust it. So that's why we use not almost almost equal. So the pipe used in practice are usually several times the length of the entrance region, and thus the flow through the pipe is often assumed to be fully developed for the entire length of the pipe. So earlier we have seen, so it's only for a very short distance for it to become a laminar, so for the velocity profile to be developed. But in our daily life, in a practical life, so we will use several times the length of the entrance region. So maybe 10 times, 20 times, 50 times. So the pipe that we are using in the industry or in the house will be several times the length of the entrance region. Okay, so we assume that the velocity profile inside is already fully developed. Okay, fully developed. Okay, so laminar flow in pipe. So laminar flow is much easier for us to estimate because it's considered like steady, incompressible flow. Okay, so but turbulent will be much harder to calculate. So consider steady laminar incompressible flow of a fluid with constant property in the fully developed region of a straight circular pipe. So we have a straight circular pipe, maybe a distance of d. Okay, so we assume the velocity profile is like a bullet, so it is a steady laminar incompressible flow. So when it's steady, laminar, and incompressible flow, so we know that it is having a constant property. So meaning the pressure will be the same, the velocity average will be the same, so the diameter will be the same, the shear stress will be the same. So everything will be the same. Okay. So in fully developed laminar flow, each fluid particle move in a constant axial velocity along the streamline, and the velocity profile UR remains unchanged in the flow direction. So I already explained this. So it will be the same throughout the flow. So there is no motion in the radial direction, and thus the velocity component in the direction normal to the pipe axis is everywhere zero. So normal to the pipe means is, so it's all pacing to in the direction of the flow. So nothing is pacing above. So to cancel the flow, so we assume it to be zero. There is no acceleration since the flow is steady and fully developed. So no acceleration, the velocity is constant. So if there's acceleration, the velocity will change. Okay, so velocity will change, but here the velocity is the same, so the acceleration also zero. Okay, so let's say we just take one small portion here to investigate. So consider a ring shape differential volume element in radius r. Okay, so radius is r, thickness dr, and length and dx are oriented coaxially by the shear stress r. Okay, so we can see there's the pressure px. Okay, so opposite direction px plus dx, because this is the dx length. Okay, then we have dr. So shear stress will be in the direction of the flow, and also shear stress plus dr. So this is based on the height. Okay, so this dr and dx we can get from this picture. Okay, so force balance of the volume element. Okay, so based on this, so we have a certain calculation. So 2 pi r is the perimeter of the pipe, so dr is the length, so p is the pressure. So for the x, so we take for all four components, so we will have this at the end, and it will become zero. Okay, so it will become zero because of this condition. So it will become everywhere zero. Okay, because it will cancel each other. Okay, but for calculation we can use this to find the force balance, so find the missing value. Okay, so 9.41, so pressure drop and heat loss. The quantity of interest in the analysis of pipe flow is the pressure drop, since it is directly related to the power requirement of the fan or pump to maintain flow. So we know earlier, so in order to generate a proper flow, so we need to use a fan or pump, okay, to create a force flow. Okay, so let's say there's some electrical failure or suddenly electrical pressure drop, then the fan also become slower suddenly, and the pump becomes slower suddenly. So there will be a pressure drop. Okay, pressure drop because it's directly related to the power requirement of the fan and to maintain the flow. Okay, so when the fan and pump having less power, so the pressure drop will be significant. So a pressure drop due to viscous effect represent an irreversible pressure loss, and it is called the pressure loss. The changes in PL. Okay, PL is pressure loss. So in practice, it is convenient to express the pressure loss for all type of fully developed internal flow, laminar or turbulent flow, circular or non-circular pipe, smooth or roughness surface, horizontal or inner pipe. So in practice, we are not really depending on this. So we will have another formula to calculate the pressure loss. And nowadays we have a lot of sensors and a computerized system which will automatically detect the pressure loss. But initially, if we as the engineer we need to calculate it in the practical way. So we need to use this formula. So changes in pressure loss equals to FL over D times with rho V average square over 2. Okay, so L is the length, D is the diameter, rho is the density, V average is average velocity over 2, and F is a constant. We call it as a Darcy friction factor. So all these values, we call it as a dynamic pressure. We will times with this Darcy friction factor. So for different material, it will have a different Darcy friction factors. Okay, so Darcy friction factor also called as Darcy Weisbach friction factor, and this value can be calculated using this information. Okay, so this is not a constant, this is a factor. Factor meaning it's a formula. So it's a formula. So F equals to 8 times the shear stress divided by rho B average, and we also have another value. So it depends on what the information we have. Okay, so 64 mu is the viscosity divided by density times weight diameter times with average velocity. So depends on the information you have, you can use one of the values, or 64 divided by the Reynolds number of the fluid. Okay, so we can get this Darcy friction factor. In the analysis of piping systems, pressure losses are commonly expressed in terms of equivalent fluid column height, called the H loss. So, or we call it as H L. So it is something related to the pressure drop also. So pressure drop, we know the pressure change is rho GH. So H, we just bring rho and G down, so we will get this formula. Okay, from here we can just try to change the initial formula that we calculate earlier. Then at the end, so the H loss can be calculated using this formula. So you just solve it and you will get this formula. FL over D, V average square over 2G. So density will not be counted inside because it will cancel each other. Okay, so the required pumping power to overcome the pressure loss is determined from, this is for the pumping power. Okay, so normally when you go to the shop, you want to buy a water pump for your house. So the shop person will ask you, so you want how many pumping power? So how many length? So everything will be related. So this pumping power can be determined using this formula. So W. So W is the power. So what? Here. So V dot. So V dot here also W dot. W dot means if you have dot, it is related to rate. Okay, so in 1 minute or 1 second, how many amount is transferred. Okay, so V is a volume flow rate times with the changes in pressure loss. Okay, so then you can use all these formulas. Okay, so this formula is related to mass flow rate. Okay, so all these two formulas can be used to calculate the pumping power before you decide which type of pump or fan you want to use. Average velocity for laminar flow in a horizontal pipe is this is also another calculation to calculate the average velocity. So this on the real life. So we already have certain formulas prepared. So the first one is negative R square over 8 mu. Okay, so divide times with P2 minus P1. So that is the pressure loss, P2 minus P1 over L. Okay, so or if we reverse it, okay, if we have information of P1 minus P2, then you can use this formula. And we also have another formula to calculate the average velocity equals to pressure change times weight diameter square over 32 viscosity times length. We can calculate the average velocity. So the volume flow rate, okay, will be dot for laminar flow through the horizontal pipe of diameter d and length l become. So this is the formula from previous chapters, chapter 6. So velocity, volume flow rate equals to average velocity times area of cross section. Then we can use the formula from the previous slide. So integrate this, then we can calculate the volume flow rate using this formula. So this equation is known as Poiseuille's law. Okay, so and this flow is called Eigen-Poiseuille flow. Okay, so we are not really studying. So you'll be studying this in thermofluid subject later. Okay, so we'll be covering more on this. Okay, so the power of the pump will be calculated using the horsepower. Okay, so horsepower is depending on the diameters of the pipe. Okay, so if the diameter is more, so the average velocity will become lesser, the power also will become lesser. So this is explained in this statement. So 9.4.2 laminar flow in non-circular pipe. So the friction factor F, okay, earlier we have calculated the resist friction factor F. Relation are given in the table for fully developed laminar flow in pipes of various cross section. Okay, so different values of D, A, and AB. So you can have a different friction factor F. Okay, so if this is 64 divided by RE, so if it's a rectangle, so if A divided by B is equals to 1, then you can use this value. So it's already calculated. Okay, calculated, so you can just use this values. So if it's a ellipse, then you can use this particular frictions. And if it's isocles triangle, okay, isocles, so it's based on the degree. So degree of theta on top. So you can have a difference in the value. Okay, all these are already calculated by the engineers for you to use your calculation. Okay, so the Reynolds number for flow in these pipes, okay, RE equals to V average DH over V is based on the hydraulic diameters. DH equals to 4 AC over V, where AC is the cross-sectional area of the pipe and P is the wetted perimeter. So this formula we already discussed in the previous slide. Okay, so with this, so we're coming to the end of the chapter number 9, and also end of the lecture for this subject. So this is the last chapter. Okay, so the summary. So today we have seen about the laminar and turbulent flow, and we have seen about the entrance region and the laminar flow in the pipe, and how we can calculate the velocity flow rate, mass flow rate using the formulas related to laminar flow in pipe. Okay, so with this, so we come to the end of our lecture today. I will take the attendance now.